So this is 2.6/2.7, rational functions and asymptotes. So rational functions are quotients of polynomial functions. So quotient meaning that we're going to be dividing. So this means that rational functions can be expressed as a division problem here, where P and Q are polynomial functions and Q cannot equal 0. So we know our denominator cannot be 0. Rational function graphs kind of look like this. We'll have asymptotes in our graph. So those are dotted lines where our graph can't cross. And then our graph kind of looks like boomerangs, like that. The domain of a rational function is the set of all real numbers except the x values that make the denominator 0.
So how would we write that? P of x, or I mean Q of x is not equal to?
Q cannot equal 0 because the denominator, but we'll find what value that is. So your domain will be all real numbers except whatever number that makes the denominator 0. All right, so domain review. Domain of a function is all real numbers except if there is a variable in the denominator. So we would set the denominator not equal to 0 because you can't get 0 in the denominator. If there's a variable under a square root, you set the expression under the square root greater than or equal to 0. And if there's a variable under a square root in the denominator, then we would know it can't be equal to 0, then it has to be greater than 0. So these are the three cases where we have to keep an eye out for our domain. So if there's a variable in the denominator, a variable under the square root, or a square root in the denominator. All right, so example 1. Yes. Yes. We've defined the domain of the rational function. So to find the domain, we know that our denominator cannot be 0. So we would set the denominator not equal to 0. And then we just solve for x. So add 4 to both sides. X cannot be equal to 4. Do I have any other restrictions on my domain I need to look out for? Any square roots? No, so we're good. So this is my only restriction. So my domain, I could write it two ways. It would be all real numbers except 4. Or I could write it in interval notation, which would be from negative infinity to 4 with the parentheses because it's not including 4, and then from 4 to infinity. Because you can't have 0 in your denominator, so that's our restriction on the domain. So our domain's all real numbers except 4. All right, example 2. How do I find the domain? Set the denominator not equal to 0. So I have x squared does not equal 36. Take the square root of both sides. So what does x not equal? Plus or minus 6. So my domain here would be all real numbers except 6 and negative 6. Or if I write it as an interval notation, I start with negative infinity and go to where? Negative 6. And then where do I pick back up again? Negative 6 to 6, and then 6 to infinity. So just remember, your domain starts with the smallest number. That's why we start with negative infinity. Then it goes until we stop, which the next number, if we were going on a number line, would be negative 6. Then we pick back up at 6. So it just starts at the smallest, goes to the biggest. All right, next we're going to look at vertical asymptotes. So if we have a equation f of x is equal to 1 over x, our vertical asymptote is on the y-axis. So that's this dotted line here that our graph gets really, really close to, but never touches. Occasionally, our graph can cross a horizontal asymptote, but it'll never cross a vertical asymptote. If our vertical asymptotes are always going to be vertical lines, but are they going to be x equals or y equals when we have a vertical line? X equals. So our vertical asymptotes will always, always, always be x equals. To find the vertical asymptote, we would just set the denominator equal to 0. So to find the vertical asymptote, we set the denominator equal to 0. So vertical asymptote goes hand in hand with domain because we know that here 0 is not in our domain and our graph gets really, really close to 0 but never touches 0. It's all the other numbers except 0. So that's why it's similar. For the domain, you set the denominator not equal to 0 because that number is not included in your domain, but whatever that number that is, that's your vertical asymptote. So here our vertical asymptote would be x is equal to 0. Next, we have arrow notation. So for our rational function graphs, they kind of look like this, little boomerangs. When it's written like this, when you see this stands for x approaches a, so it'll be some value a, from the right. So positive, you're coming from the right direction this way. Thank you. When it has a little negative sign over it, x approaches a from the left. So it would be talking about this part. So you're approaching that value coming from the left. All right, so for the next one, the equation f of x is equal to 1 over x squared. The vertical asymptote is on the y-axis. So it kind of just gives us the answer here. But to find the vertical asymptote, we set the denominator equal to 0. So what's x equal to? Bless you. X is equal to 0. So this would be our vertical asymptote. Bless you. So our graph is going to get really, really close to this dotted line here, but never touch it, never cross it. So this is our equation of our graph. How do we find the vertical asymptote? Equal the denominator to 0. So we have x squared minus 9 equals 0. Then I solve for x. So add 9 to both sides. X squared is equal to 9. Take the square root. So what's x equal to? Plus or minus 3. So I have two vertical asymptotes, one at x is equal to negative 3 and one at x is equal to positive 3. So here, they're graphed for me already. I have a vertical asymptote at negative 3 and a vertical asymptote at positive 3. So this is an example where we have two vertical asymptotes.
You just draw the line like that, or like space out. Like, it's not just like one solid line.
Right. It's just like a dotted line because it's not part of your graph. It's just showing you that your graph is going to get close to that line, but it's not going to cross. So for the next one. For the third one, C. I set the denominator equal to 0 to find my vertical asymptote. So I have x squared plus 9 is equal to 0. Solve for x. X squared, thank you, is equal to negative 9. What do I do next? Take the square root. So what's x equal to? Plus or minus 3i. When you have an I in your answer, there's no vertical asymptote. So here we would have no vertical asymptotes because we only want to deal with real numbers now, not with i's. So there's no real number here that would make the denominator 0. So we have no vertical asymptote. So to find our whole, we have to factor the top and factor the bottom, see if anything repeats. So the top is factored, we have x plus 3. I can factor the bottom here. What are two factors of negative 9 that add to 0? X plus 3, x minus 3. So what repeats? The plus 3's repeat. So I would have a whole at x plus 3 is equal to 0. So at negative 3, I have a whole. So if you look on my graph here, at negative 3, there's a whole. Right, so here our vertical asymptote would only be x is equal to 3 because you can't have a vertical asymptote through a hole. The hole is just where your graph doesn't exist. So for horizontal asymptotes, we're looking at the degree of our numerator and the denominator. If the degree of our numerator is smaller than the degree of the denominator, then our graph has a horizontal asymptote at y is equal to 0. So if I had x squared over x cubed, my degree of my numerator is 2, and my degree of the denominator is 3. So since 2 is less than 3, I have a horizontal asymptote at y is equal to 0.
So whenever the denominator is bigger?
Whenever the denominator is bigger, y is equal to 0. That's your horizontal asymptote. If they're the same, so if I had, let's say, 2x squared over 4x squared, so if our degrees are the same, your horizontal asymptote comes from the coefficient in front of those highest degrees. So here, our horizontal asymptote would be 2 over 4, which simplifies to what? 1/2. So it would be y is equal to 1/2. Because for horizontal lines, we have y is equal to. So you're just looking at the coefficients when your degrees are equal. And then if the degree of your numerator is higher than the degree of your denominator, you have no horizontal asymptote. So if we had x cubed over x squared, this would be no horizontal asymptote. So our equation for this first graph is in this box. So to find horizontal asymptotes, we're looking at the degrees of our highest term in the numerator and the denominator. So what's the degree of the highest term in our numerator? 1, because here it's just x, so that would be x to the first power since it doesn't have a degree. What's the degree of our highest term in the denominator? 2. Is 1 greater than, less than, or equal to 2? It's less than. So what happens when our numerator is less than the denominator? Y equals 0 is our horizontal asymptote. For the next one, again, we're looking at the degrees here. So what's the degree of our numerator? 2. And what's the degree of our denominator? 2. Is 2 greater than, less than, or equal to 2? Equal. So what happens when they're equal? You take the coefficients and put them over each other. So the one that's on top is already on top, so you just make a little fraction with it. So we have 4 over 2. So this would simplify to 2. So our horizontal asymptote is y is equal to 2. Y equals.
Would you draw it like the same way as like the vertical one, like spaced out?
Yeah, with the little dotted line. So like here, it's drawn for you. All right, for the last one, what's the degree of our highest term in our numerator? 3. And our denominator? 2. So 3 would be greater than 2. So what happens when your numerator is greater than? We have no horizontal asymptotes. Here we have to find the horizontal and vertical asymptotes, if there are any, for each. So how do we find, let's start with the vertical asymptotes first. How do we find the vertical asymptotes? Set what equal to 0? Set the denominator equal to 0. So our denominator is equal to 0. Can you see the green on there? Okay. Add 36 to both sides. So x squared is equal to 36. Take the square root. So what's x equal to?
6 plus or minus.
Plus or minus 6. So we have two vertical asymptotes at positive 6 and negative 6. Now let's find our horizontal asymptotes. So horizontal asymptotes, I'm looking at what? The degree. So what's my degree of my numerator? 1. And what's the degree of my denominator?
2.
So 1 is less than 2, so what does that mean my horizontal asymptote is? Y equals 0.
Could you have more than one horizontal asymptote?
Alright, let's look at B
Are we gonna be graphing them today?
tomorrow. So to find our vertical asymptote, what do we do?
Set the denominator equal to 0.
Set the denominator equal to 0. So x squared is equal to 4. Take the square root. So what's x equal to? Plus or minus 2. So that's our vertical asymptote. Now let's find our horizontal asymptote. So I'm looking at the degree for horizontal asymptote.
They're both the same.
They're the same. So what do I do? 3 over 1. Awesome. So y equals 3. So like since this is x squared and this is x squared, you're looking at 3 and you're looking at 1. So 3 over 1 gave us 3. All right, and then last one, C down here. What do I do for the vertical asymptote? Set the denominator equal to 0. So I get x squared is equal to negative 1. Take the square root. So what's x equal to? Plus or minus I. So what's my vertical asymptote? No vertical asymptote. And then how do I find my horizontal asymptote? The degrees. So I have the degree of what on top? 1, and the degree of 2 on the bottom. So if 1 is less than 2, what's my horizontal asymptote? Y equals 0. Next, we're going to look at holes. Sometimes we have holes in our graph. To find a hole, you always want to factor the top and the bottom, and whatever repeats on the top and the bottom. So here we had x minus 2 and x minus 2 that repeated, so they canceled each other out, but at that point we have a hole. So we would set x minus 2 equal to 0. So x is equal to 2 is where we have a hole. So where x is 2 on our graph here, there is a hole. So to find our domain, we would set the denominator not equal to 0. So we know that x cannot be 2. So we would account for that in our domain. That's why that point is not in our domain. So the graph of a rational function has a slant asymptote if the degree of the numerator is 1 more than the degree of the denominator. The equation of the slant asymptote can be found by division. So it's the equation of the dividend with the term containing the remainder dropped. So our slant asymptote is just the whole number part of what we divide. The remainder's not included. So the remainder doesn't matter with your slant asymptotes. It's just everything you get before the remainder. So looking at example 6. So because our degree on top is 1 degree bigger than the degree in the bottom, we could have a slant asymptote, so we need to divide. So it's always what's on top that goes inside the box. So this would be x squared plus 6x plus 2 divided by x.
You're doing long division?
Long division. So what times x gives us x squared? X. So then multiply x times x, so we get x squared. What do I have to do next? Change the sign and combine. So those cancel, and then I just have 6x. So what times x gives us 6x? 6. Multiply 6x, change the sign, they cancel. Then drop the 2. My remainder is 2. But I'm just looking at the whole number part here for my slant asymptote. So my slant asymptote, SA, would be y is equal to x plus 6.
Oh, so it's that whole thing.
And it has to be y is equal to that, because it's an equation of a line. Your slant asymptote is some slanted line. If we had a graph here, how do we graph y is equal to x plus 6?
Start at 6.
I start at 6, 1, 2, 3, 4, 5, 6, because that's my y-intercept, and I would go up 1 to the right 1, and my slant asymptote would be there. So it has to be y equals because it's a line. Let's say we just had a vertical asymptote here also. Well, we have a vertical asymptote at 0, right? Because we would set the denominator equal to 0, so our vertical asymptote goes through here. So our graph is the boomerang shape, so it'll either be like in here and in here, or it could either be in here or in here.
How do you know it's boomerang shape?
Because that's what all of our rational function graphs are.
Okay, so this is just another asymptote that I
Just another asymptote. All right, example 7. Again, we're finding the slant asymptote. So because our degree of our numerator is just 1 bigger than the degree of the denominator, we have to find the slant asymptote. What's going to go inside the box? X cubed plus 0x squared plus 0x minus 1. You need those placeholders in there. Especially when it's inside the box, you have to have those zeros there. And then outside, we have x squared plus 2x plus 2. So what times x squared gives us x cubed? X. So I'm going to put that x over the x column. Then I multiply. X times x squared is x cubed. X times 2x is 2x squared. And x times 2 is 2x. Change a sign, change a sign, change a sign, and combine. So this would be negative 2x squared minus 2x. So what times x squared gives us negative 2x squared? Minus 2. Then we multiply. Negative 2x squared. Negative 2 times 2x would be negative 4x minus 4. Change a sign, change a sign, change a sign. These cancel. Combine 2x plus 3. What's next? That's the remainder. And we don't really care about it.
Isn't it 2x plus 3? Like, I mean, plus 4. No, sorry.
So our slant asymptote is y equals x minus 2. On this last slide, it's a cheat sheet. So to find the domain, you set the denominator not equal to 0. To find the vertical asymptotes, you set the denominator equal to 0. Remember, vertical asymptotes are always x equals. Should be x equals. Horizontal asymptotes, you look at the degree of the leading coefficients. So if the degree of the numerator is bigger than the degree of the denominator, there's no horizontal asymptotes. If they're the same degree, you're looking at the leading coefficient of the numerator over the leading coefficient of the denominator. If the numerator degree is smaller, then y equals 0. So your horizontal asymptotes are always y equals. Slant asymptotes, you use long division. Again, your slant asymptotes is y equals. And then we're going to get to finding the y-intercepts and x-intercepts tomorrow, but it's the same thing that we've been doing. For the y-intercepts, you set x equal to 0. X-intercepts, you set y equal to 0. And then the wholes, you factor the numerator and the denominator, cross the common factors, and set them equal to 0.